Lewis dot diagrams, or Lewis structures, give us a reliable and fast procedure to estimate how atoms are bonded together in a molecule, and they also give us a convenient, reasonably accurate way to visualize them. For instance, just look at these atomic force microscopy images. They look pretty much identical to how we would draw them according to their Lewis structures. The first step in the procedure is to determine whether the molecule is ionic or covalently bonded. You do this by determining the difference in electronegativity between the two atoms in the bond. Two of the same atom bonded together are going to have no electronegativity difference at all, so like hydrogen and oxygen gas will be perfectly covalent. Different atoms sharing a bond will produce a difference in electronegativity, and the greater the difference, the more ionic the character in the bond. Most of the ionic compounds we'll see on this course pair a metal and a nonmetal, like barium bromide or gallium sulfide. For an in-depth discussion on creating Lewis dot diagrams for ionic compounds, please watch our other video on the topic listed in the description. For today's example, we're going to find the Lewis structure for cyanogen, C2N2. Now this molecule is primarily used as a rocket propellant, but it's also considered a chemical weapon because it easily decomposes into cyanide, a blood agent that suffocates you on the molecular level. Our first step will be to tally up how many valence electrons we have in this molecule. So with 2 carbons, that gives us 8 electrons, and 2 nitrogen give us 10 electrons for 18 electrons in total. That's our electron budget that we can use to build the molecule. Next we have to decide which atoms are going to be central and which are going to be on the outside, or the terminal atoms in this molecule. We decide that by saying that the atoms with the lowest electronegativity are more likely to be the central atoms. In this case, that's carbon. So we'll put both carbons in the center of the molecule. Now we have to decide how we're going to arrange nitrogens. We can put them both on one side in a string, or we can stack them up on top of one carbon. But as a general rule, nature likes symmetry, so we'll arrange it so that there's one nitrogen for each carbon atom. Next, we'll place a single bond between each of these atoms and subtract 2 electrons per bond from our total budget, leaving us with 12 electrons to deal with. Those we're going to arrange around the atoms, starting with the terminal ones first, and then working our way towards the central atoms. So we place 1, 2, 3, 4, 5, 6 electrons around one nitrogen, and we do the same on the other side for symmetry's sake. And that takes away all of the electrons left in our budget. So let's subtract 12 from 12, leaving us with 0 electrons left. Next we can check the octet rule on each of the atoms. So if we count each bond as contributing 2 electrons to each of the atoms that the bond connects to, for the first nitrogen we have 1, 2, 3, 4, 5, 6 lone pair electrons around it, plus 2 on the bond. So that's 8. So that nitrogen is good. Same thing on the other side. But the carbon only has 2 and 4 from the 2 bonds that come out of it. Well, we can take some of the lone pairs on the nitrogens and turn them into bonds with the carbons, so that the nitrogen still has its 2 electrons attributed to it in the bond, so it keeps satisfying the octet rule. But now each of the carbon also has 4 bonds, or 8 electrons attributed to it, so it also satisfies the octet rule. You now have a plausible Lewis structure for cyanogen. Stopping at this point means that we're leaving some information about the atom on the table. We haven't considered everything we know about it, and this could mislead us into accepting an incorrect structure. So we'll discuss these other considerations throughout this week.